Hi everyone, welcome once again to our series on basic mechanics. Kindly subscribe, like, share, leave your comments and suggestions at the comment section. Today we are looking at replacing a system of forces with a force couple system. 2D, example 1. Let us look at our question and see how we are going to solve it. Replace the force system acting on the frame by an equivalent resultant force and couple moment acting at point M. Replace the equivalent force couple system at T. Let's look at how to solve this kind of questions. Good. How are we going to solve this question? Like this, which we have been given. Now, with this question, since it is a 2D object, we are going to use the scalar approach. So it means that if we have asked to find the force couple system in this diagram, it means that we want to represent all the forces there with a resultant force and also with a resultant moment at where we have been asked to find our force couple system. So in this case, we are asked to find the force couple system at point M. Point M, this is where we are finding our force couple system. So quickly, let's look at how to solve this. I've already told you that since it's two-dimensional, we are going to use the scalar approach. So first of all, let us find the resultant force. But don't forget that for you to the resultant force. But for you to determine the resultant force, first of all, look at these forces here. This force is at an angle. We cannot see this force in the X or in the Y, and the same applies to this force here. We cannot say that it is in the X or it's in the Y. So anytime you are given a force like that, you resolve such forces into components, which is X and Y component. So let's see how to resolve this force here into components. It is like this. So you can see that from this diagram, the force, the starting point of the force is here, and this part is the ending part. Therefore, it means that if you want to move from the starting point to where we are ending, we are going to move this direction on the X and this direction down here on the Y. This direction on X and this direction on Y. So from here, you can see that with respect to this angle, our Y will still be at this side, our X will be at that side. So it means that if we draw that force diagram, we are going to get something like this. And this will be our Y, and this will be our X. This will be our X. If we draw that diagram. And we are told that the angle here is 35. Therefore, we can say that because our Y component, look at it, if we want to move from this point to that point, we'll be coming down on the Y. So our Y component is going to be negative, the force there is 450, so negative 40. And you can see that the angle is facing this side. The angle is facing this side, so negative 450 sine 35. And our X component will be this side. we said that from here you'll be moving this direction, which is positive in this direction. So our S component, you can see that it is adjacent to the angle. It will be 450 cos 35. And from here, you can see that our f of x for that force will be 450 cos 35, which will be equal to 368.6 newtons. And then we can get our y component for that force as 450 sine 35. And from there, our answer will be negative. Don't forget that we said that it will be negative because if we are moving from this point to that point, we'll be moving downwards. So this will be negative, which will give us negative 258.1 newtons. So we have resolved this force into components. Now let's come to this force here. So you can see that this force here can also be drawn like this. This is our force. So this is the starting point and this is the ending point. So this is our starting point and this is our ending point. You can see that if you want to resolve this, you are going to move this direction on the x, and this direction is in the same direction with our positive x-axis. Positive x-axis. Don't forget this. So this x will be positive and y also will be moving up. From here, will be moving up like this. So all of them, this side will be positive, this side will also be positive. And this is our angle, which is 60 degrees. So if that is 60 degrees, you can see that the angle is adjacent to our x. The angle is adjacent to our x. So you can see that for that force, and we know that the value here is 310. 310. So the x component for that force is going to be 310. This side is adjacent to the angle. So cos 60 will be equal to 1155 newtons. And then we can get our y component for that force also, which will be 310. Now you can see that this is a y component. The y component is facing the angle, which is going to be 310 sine 60, and that will be equal to 268.5. 268.5. And from there, we have also been able to resolve that force into x and y component. Therefore, for us to get the resultant force, we need to sum all the s components or the forces in the x-axis together, and we also sum the forces in the y-axis together. Therefore, let's sum the forces in the x-axis together and see that anytime you are moving to the right, it's positive. So we have x for this force here, it's moving in this direction, it's positive. It will give us 650 plus, sorry, this is not equal to 0, 650 plus, we have the s component for this force, and we said that it will be moving this direction also, and we said that this direction is positive, which is going to give us positive, which is going to give us 368.6 plus our s component for this force here, which is 155 newtons. So from here, sum of f of x will be equal to 1173.6 newton I s component, and then we can sum all the y component also. Y, we take it that anytime we are moving up, it's positive. So from here, our y have this, which is already here, but look at it, it's coming down, so negative 200. The y component of this, we said that it will be moving up, so it's going to be positive, to give us plus 268.5. And the y component of this force here, look at it, we said that the y component will be coming down, which is negative. So you are going to get negative, and the value is 258, negative 258.1. And from here, our sum of y is going to be 210.4. So it means that our resultant force, which is equal to Rxi plus Ryj, will be equal to 1173.6 I plus 210.4. But This one is in the vector form. What will be the magnitude of this? What will be the magnitude of this? So the magnitude will be r is equal to square root of 1173.6 squared plus 210 squared. And from here we can get the magnitude of our resultant force, which will be equal to 1192.3 newtons. So we have gotten our resultant force. Now we are left with our resultant moment. So from here, we are asked to find the force coupled system at M. So it means that we are going to take our moment at M, where we want to put our force coupled system. So let's see how to determine our moment. So sum of moment at M. And let's take the anti-clockwise to be positive. So from here, we can say that we take each of the forces and then we multiply it by the relative distance. So here, the force here, we know that we have the x component. Sorry, we have the x component, and then we have the y component like this. I have the x component here like this, and the y component here like this. And we are taking our moment at M. But don't forget that moment is always the force times the perpendicular distance. And we are using the scalar approach to check whether it will be clockwise or anti-clockwise, and the direction will not matter. So here the y for this force is here. And we know that this is 268.5, and the s component there is 155. Good. And the s component for the y component for this side, let me clean so that we can see very clearly. So for this side, we have the y component coming down like this, and then we have the s component like this. And then the y component is negative 258, and the s component is 368.6. So we pick this force and we multiply by perpendicular distance to where we are taking our moment. So the perpendicular distance will be this distance from here, which will be 0.8 plus 0.3. Therefore, we are going to get 268.5 times 1.1. And we said that we check whether it will be clockwise or anti-clockwise. So the distance is here. And by the principle of transmissibility, this force here can be written as this. So you can see that if you have force here and the distance is here, it will rotate. This point is fixed. So it will rotate this object in this direction, which will be anti-clockwise, and that will be positive, plus the s component here, which is 155. You can see that the s component is lying on this line. So the perpendicular distance where we are taking the moment is going to be the vertical distance from this point to that point, from this point to that point, which is going to give us 155 times 0.6 plus 1.3, which is 1.9. But now let's check whether it will be clockwise or anti-clockwise. So this is the perpendicular distance, and this is our force. So from the principle of transmissibility, if this is the distance, our force can be written like this. What is here can be written like that. So this one, you can see that our rotation will be like this, which is going to be in the anti-clockwise. That is why it is positive. Then we come to our force here. So this one is vertical. The perpendicular distance will be on the x-axis. Because it is on the y, the perpendicular distance is going to be on the x. So this will be times 0.8. So we have 200 times 0.8. But is it going to be clockwise or anti-clockwise? So by the principle of transmissibility, this force can be placed here. So if you have the distance like this and the force is here, and this is where we are taking our moment from, then this is going to rotate object in this direction like this, which will be clockwise. So what is here is going to be negative. And then we have plus. Now we have one force here. So where we are taking our moment. So this is a horizontal force. Therefore, the perpendicular distance will be a vertical distance. vertical distance. We are going to get 650 times the perpendicular distance from this point to where we are taking our moment, which is also 1.9. And then plus. Now you can see that the forces here, you have x. So the x component, this is a horizontal component. So the perpendicular distance where we are taking our moment will be from this point to that point, which is 0.6. So we are going to get 368.6 times 0.6. But now you can see that if the distance is here and the force is applied here, it is going to rotate the object in this direction. This side is fixed, which is going to be anti-clockwise. Therefore, it's going to be positive. And then the last thing, look at this force here, this vertical component for this force. You can see that it is on the same line of action with where we are taking our moment. If I clean that side, you see that the vertical distance for that force will be like this. And it is in the same line of action with where we are taking our moment. They are all on the same line of action here. Therefore, we are not going to get any moment for our vertical force here. So from here, we can just simplify and say that our resultant moment is going to be 1085.65 Newton meter. So our force coupled system at M, is going to be like this. We are going to have, so all the forces on this system can just be reduced to a single force and a single moment at M. And we are saying that it is going to give us, the single force is going to give us the resultant. The resultant of that force will be 1192.3, and the moment is going to be 1885.65 Newton per meter. So with this, we have reduced all the forces here to only one single force and one moment. So that is the A part of the question. And the B part of the question was saying that we should remove this resultant, we should remove this force coupled system from point M and bring it to point P. But don't forget that our force here was made up of two components. Don't forget that our force was made up of two components, the S component and the Y component. So it means that here our resultant, we are going to have one component like this and another component for this like that. So we are going to get a component here and a component there. They were all positive. So our resultant should go this direction. The resultant should move this direction. Good. So if this is the case, then we said our resultant will be like this. So this is the S component, the Y component, and this is our moment. Don't forget, if you want to remove this force coupled system from M and bring it to P, moment is a free vector. So we can easily remove our moment from that point and bring it here as 1185.65. It's a free vector. So we can easily remove and bring it here. But we cannot remove our forces, the S component of the force and the Y component of the force here, and bring it to this point. We said that once the force moves from its line of action to a new point, we need to add a corresponding moment. So if you want to remove this S component and this Y component of the resultant force here to point P, then because we are moving them from their line of action, we should multiply, or we should get another moment which will be equal to the force here, and is a distance from this point here to the original point where the forces were. So from here, you can see that the Y component will be on the same line of action with P. So even if we bring it at this point, the y component will still be in the same line of action. Therefore, it means that the y component is not going to get any moment, but the s component here is going to get moment. So it means that our resultant moment at P is going to be the original moment there plus the moment which the s component is going to create. So we know that the line of action of the s component will be in this direction, but the line of action for the y component will be at this direction. So even if you bring at P, the y component has not changed its line of action. So the only thing we are going to change its line of action is for the s component. Therefore, it means that you add a moment for the s component, which is going to be 1173.6 times the distance from our new point here to where the force was originally applied. So we'll be moving up, which is positive. So we are going to get 0.6 plus 1.3, and that is going to give us a total moment of 411.49. So at P, our resultant force, the resultant force will still be our I component, which is 1173.6 I plus our y component, which will be 210.4, and then our resultant moment is going to be 4115.49.49. Good. So that is how to move the resultant couple from one point to another point. And that was very easy. I don't know how you see it, but the question was very easy to solve and very simple to understand. But if you have any question, any suggestion or anything, you can let us know at the comment section. Once again, thank you very much for watching. Kindly subscribe to our channel and hit the notification bell. See you once again in our next video.